All right, so in the tutorial, the first three questions that we'll be trying out today will be finding the inverse Laplace of three given functions, and then find the solution of the differential equation, given differential equation using Laplace, and then we have the transfer function of a system, and we'll be like finding certain parameters such as the rise time, peak overshoot, and settling time based on the model that we get, right? Okay, so Laplace will go with the first sum. Okay, so we have been given this model, right? So now, so I will be using the Laplace table given to you all by Sir, right? So for this module, I recommend you all use that table. Right? So I will share that table as well. Okay, so we'll be using this table. I think this is the one that has been given, right? So this is the table that you all have been given. So we'll be using this table. So that, I mean, that's much more easier because, like, let's say if you want to like use one of these equations, we can just simply refer to the number, right? So we can just tell you all what the number is because these are actually quite similar to each other. Now, let's say if you have like take these two. Now here it's like here you have S on top, and here you have omega n squared on top, right? So like sometimes you might like mistake these and substitute the wrong values and get the wrong answer. Just much more easier for us to like refer to these equations by the number. So it's much more convenient for both of us, right? So now let's talk about right. And also I'll be using this board here. I have not tried this because I have been using one more, but the thing is crashing. So I'll be trying this out the first time. So if this doesn't work out, we'll go to the whiteboard of the soup, right? Okay, so we'll start with the first sum. So we have been given. So any idea how to solve this? How we can proceed? Actually, there's two methods, right? To solve this, there's actually there is a white. So, yeah, I'll just go to the whiteboard. That's a small. Okay, so if we take this equation, right? So this is what we have been given, right? So this is already in the what do you call the S domain, right? So if not, you can call it the Laplacian domain, or you can call it the frequency domain, right? So you can call it whatever you want. So why we need this domain? Why we need the Laplacian domain is like it's much more convenient for us to do certain processing for our system in the frequency domain, right? It's much more convenient and it's much more easy. And most of these theories that we use are valid inside this frequency domain. You can, of course, do all this in the time domain as well, but it's much more easier to do it in the frequency domain. But when you are doing modeling in the frequency domain, we have to always convert it into the time domain, because we are building our systems in time domain, right? We don't have any electrical circuits or any controllers in the frequency domain, physical controllers, right? We have to build that in the time domain. So to do that, we have to we have to convert whatever the time domain equation into the Laplace domain, do the processing, and then we can get the inverse Laplace, and then model it in what do you call the the, the time domain, right? So that's what we'll be doing here, right? So I'll just go with the method 1 first, right? So method 1. So method 1 we'll be using okay. So method 1. So you all know the linearity property of the inverse Laplace transform, right? So this entire system now. So if you want to get the inverse Laplace of this, right? Let's say if we have like ys, right? And if it's equal to something like a fs ts. Now we are not going to derive any of these. So that's actually like I mean something that needs to be covered in a mathematics program. But we'll be like using the application. We'll be like focusing about the applications of this, right? So what we can do is, if we want to get ys, we can take a out, right? Because a is a constant, right? So a and b are like constants, right? So so what we can do is we can like get the Laplacian, inverse Laplacian of fs, plus we can get b out, and we can get the inverse Laplacian of g's, right? So we can use the same thing here, right? So we can use the same thing here. So what we can do is we can get this s plus 3 plus 1 s plus 2 as. Now to do that, first, now you can see now here this. Now always when you're like trying to get the inverse Laplace, you should like refer the table. So if you look at the table, if you look at the table, if I go to the table, let me know if there's the stuff that I'm sharing, if they are not visible, let me know. Okay. So if I go to the table, right? So we can use this, right? We can use this. We can use this like convert it into our time domain, right? To do that, we should have so we have, like, if you look at our equation, it has an s and a constant, right? So the best way, one thing that we can do is we can like divide this into two parts, right? So one, we can have the s part on top, and the other one we can have the constant on top, right? So if we have the s part and the constant on top, we can use this and this, right? So we can use 15 and 16 to convert our function which in the Laplace, which is in the frequency domain, to the time domain, right? So so what we can do is, so yeah, our plan is to like use 15 and 16, right? So I will go to a new system. So I will get this here, this one here. So what I can do is I can like get the small incline in this, I don't know. Must Laplace of S over S plus 1, S plus 2, right? Plus the inverse Laplacian of 3 over S plus 1, S plus 2, right? Okay, so now I'll get another page to this part. So now we'll first solve this part, right? So first solve this part where we have S on top. Let me know if anything is not clear, okay? It's not like the lecture starts. Tutor also you all have to be tracked. So what we can do is we can use the 16th so if you use the 16th I mean the transform, we know that so S plus A S plus B is equal to 1 over B minus A BE minus BT, right? So we'll be using this particular transform. So we know in this equation we have our S, we have our A, and we have a B. So our A is 1 and our B is 2, right? So if I just and our B minus A, right? So if I just substitute these values in our equation, we can get that 1 over 1. This is B is 2, 2E minus 2T minus E minus T. So simply this part we can get as 2E minus 2T minus E minus T, right? Okay, so we have one part covered, right? So we have one part covered. Now we just go to the other part right here, so it's much more easier for us to refer this, okay? So here what we'll be looking at is the inverse Laplacian of constant of 3 S plus 1 plus 2, right? So for this we can use the equation 15, right? That's what we solve. 15. So 15 actually tells that whatever this is 1 over B minus A. So basically it's like there's E minus AT minus E minus B, right? So we'll just substitute that to the equation. Okay. We substitute this first because we know our A is 1 here and B is 2 here. So substitute. So it's the equation. So 1 over S plus A. So we can. So we are once again using the linearity property of Laplace. So it has to be 1 here, right? We should have 1 here. We should have 1 here. So to have 1 here, what we can do is we can get this 3 out, right? We can get this 3 out. So this is in the format that we want. So to have 1 here, we can get this 3 out. That's actually the linearity property of Laplacian or inverse Laplacian. So we get 3 out. So we get E A is 1, so it's minus t, right? Minus e minus 2t, right? So actually we have this part here. So what we need is the addition of these two, right? It looks like a multiplication. We need the addition of these two. Okay. So if we get the addition of these two, we actually have the inverse Laplacian of the given function, right? So simply inverse Laplacian of this, right, would simply be 2e minus 2t minus e minus t. And if we get this part, that's 3e minus t minus 3 minus 2t, right? I will open a separate portal in CourseWeb for these parts, right? So the ones that I do here also, you just do and submit just so that I know that you guys are like involved in this, right? I mean, within the day, maybe by tonight. Because of course, if we had this on campus, we could have like checked your work, but since we can't do that, right? So we can get these two together, right? And these two together, right? So we'll have, from this we'll have 2e minus t minus t, then e minus 2t, right? This is our answer. So we have this function as a function. So like earlier page, we have this part converted into the time domain as this, right? I hope that this is clear, right? This is very easy. So this is one method that we can do this, right? This one method that we can do this, since this is like introduction for your class, and I will quickly do the other method as well. So the other method is actually we can use partial fractions, right? You know partial fractions, right? Now remember partial fractions from your A levels. Right? I think you all have done this for like integration in functional maths, right? So the method 2, we can use partial functions, right? So now once again our function is this. I am teaching out both these methods not because you have to solve this in both the ways, but like there are occasions where it's much more easier for you to use partial fractions. Sometimes it's much more easier for you to use like the normal method, right? Conventional method. Actually, there's no conventional method, like you can use anything, right? As long as you get the exact correct equation, right? Correct answer. So we can write this as a over s plus 1 plus b over s plus 2, right? Then by cross multiplying, you can get s plus 2 b over plus 1, and if we like equate the coefficients, we can find so it's, if we like get this, we can get one equation as plus b plus 1, right? And we can get another as 2a plus b equals 3. So by like substituting substituting one of 2, we can get a is equal to 2 and b is equal to minus 1, right? So now if we like get the, now we know this, now we can rewrite these as s plus 3 s plus 1 plus 2. Right? And here it says 2 over s plus 1. B is minus 1 is 1 over s plus 2. Now we can get the inverse Laplacian, this entire, right? This part and this part, right? It's got a bit messy, but you get the idea, right? So, so if we like get this thing, so if we get this part, we have 2 over s plus 1 here. So we can get 2 out, right? We can get 2 out, and we have 1 over s plus 1. What is this? We go to our table. We can see that 1 over s plus a is equal to e to the power minus 80, right? So we know our a. So I go back to the screen. You guys are with me, right? Are you all like listening?
Yes, sir.
So we know that 1 over s plus a is equal to e to the power minus 80, right? So we know our a is equal to 1. So if we just simply transform this, we'll get 2 from here, e minus t, right? So we have one part. So the other part I will just do here because we don't need much space for that, right? If we get this part and we get the inverse Laplacian of I think b is minus 1, so minus 1 over s plus 2. Right? So our this thing is our a is 2, right? So it's minus e because of this minus 2t, right? So we like combine these two together. We like combine these two together, we get e to the power minus 80. So you should have the 2 here, right? The 2 I have lost. I mean, it's there. Sorry, so it's not 80, it's minus t. Minus e minus 2t, right? So this is what we get. So if we go back to the other method, you could see that we have got the same answer, right? Yeah. 2 methods, but same answer. Okay. So as long as you get the answer properly, you can use any method, right? Okay. So we go to the next sum. Next sum, of course, says so it's a second order function, right? It's a second order system. Now, when you look at this, so when you have like a quadratic equation in the bottom, just give me a second, I'm getting a call. Right, sorry. So yeah, so when we have like a function like this, right? So the first thing, when you have like a quadratic equation as your denominator, first thing you have to do is you have to find the poles, right? Poles are like the roots of the denominator. You all have done what poles are, right? So you should first find out what the roots are or the poles are of the denominator. So we'll first do that. And also, you know from your A levels, right? You all know from your A levels. So if you have like a quadratic function like x, it's my video of like x squared plus bx plus c equals 0. To find out where the roots of this exist, right? What we do is we get b squared minus 4ac, right? And we can check the availability of roots. If let's say if b squared minus 4ac is equal to 0, how many roots do we have? How many roots do we have if this is like this? As you need to answer. Sorry? How many roots?
1.
Yeah, that's one, right? So something like this, and we have just one root here, right? And if b squared minus 4ac is greater than 0, we have something like this, right? And we have 2 roots. And if b squared minus 4ac is less than 0, we have something like this, and we have no roots. Actually, we don't have any real roots. We have complex roots, right? We have complex roots. Right. So in this case, we have this function. We have 2s plus 12 over s squared plus 2s plus 5, right? So this is our function in this domain. So now if you want to check this, so if you get the b squared minus 4ac of this, you will find out that this is negative, right? So it's actually, if you get the b squared minus 4ac of this will actually give 4 minus 20, that's minus 16, that's actually less than 0. So this has complex roots, right? So when you have complex roots, if I go to the table, I go to the Laplace table here. So Laplace table here. Yes, I had to stop sharing the screen. So if I go to the Laplace table here, right? So we actually use if we have complex roots, we use the transforms available from this point onwards, right? So we have this omega here, right? From there only we start using this the Laplacians if we have like a complex root, right? So if we use something else from the beginning, from the top, that will actually give you like a wrong value, right? So you should always use values from this point onwards, because this s, right? The s that we use here. So if I go back to this part, so the s that we use here, right? The s, whatever we use in this domain, is equal to sigma plus j omega, right? And if we actually plot this, if we actually plot this as a vector, and if we take this as the imaginary part, the real part, this part is equal to sigma, right? And this part is equal to j omega, right? So this is actually the imaginary value. Omega is actually the coefficient that comes with the imaginary part, right? So this is as a vector. This we can get as phi, right? So That's why actually we have the omega. If we don't have the omega, that means it just has the real part, right? It's just going through this real axis, and its imaginary component is 0, right? By any chance, if we have like imaginary component, then this omega comes into play. I hope that's clear. Okay, so that's why we actually. So I just want to explain why we are using that. I mean, you might wonder why we are using equations from 20 onwards for complex. That's the reason. Okay. So if I go back to the table, right? So these equations has omega are what we use when we have complex roots, right, or complex poles in our equation, right? Okay, so I go back to the whiteboard, right? Where were we? So we have that this is 0. This is imaginary. So what we can do is we can use the equations 23 and 22 here, right? We can use the equations 23 and 22 from the table. So 23 actually says when there's an s on top of as the numerator, and here when you have omega n squared, right, on top. So we can like separate our equation accordingly, because our function has both an s part and a constant part, right? So here the constant actually has to match omega n square, right? You can't just make it 1 and use it, right? So here you know that we have to match this exact format, right? This is like some sort of template. So we have to match our function in this template format to fit in our system, right? So if I go back to the whiteboard, let me know if anything is unclear, because we have to get the fundamentals properly to continue, right? So we can like get 2s plus 12 by squared plus 2s plus 5. So we have here, we can get 2s separately, right? We can get 2s separately over square plus 2s plus 5. And this part we can actually get solved using the equation number 23, transform number 23, because there's an s on top. We can get this 2 out using the linearity feature of Laplace, inverse Laplace. And then this 12, we can, as a constant, can get here plus 5. All right. So for this, we can use equation transform number 22. Just check whether it's correct again. I'm referring to my printed table here. Okay. So now this is one way. You can substitute and solve this using this, but it might be a little bit tricky, because there's a lot of elements in your equation. This one way, right? You can just simply substitute these values and kill it. But there's another way which I will do, which is actually the much more easier way, right? So this is method 2, right? This is method 2. All right. So method 2, I will get the same function. Same function, that is plus 12 over squared plus 2s plus 5, right? So what we can do is, we know this part. We can write it like this, right? We can write this part as plus 1 squared, right? So if you write s plus 1 squared, you will get s squared plus 2s plus 1, right? So we got s squared plus 2s plus 5. So to counter that, we can add another 4, right? So we got s squared plus 2s plus 1 plus 4. That will give us this, right? Everyone's clear with that, right? Okay. So now we can. So now we got this. Now if you write it, if you write face, we got this. We can write. We can break this down also, right? We can break this down also. Now actually I'm referring to the equation. Okay, I'm referring to the the format that we have to get from the table to get the desired output, right? So so what I can do is I can write this, the top part, the 2s plus 12, I can write it as, I can get the 2 out and can write it as s plus 1, right? So s plus 1 give me 2s plus 2. To get the 12 here, I have to add another 10, right? There's nothing confusing, right? If you expand this, you will get the same thing. And the bottom part, I can write it as s plus 1 squared plus 4. Now, if we go back to the table, you can see that we are slightly getting the required format. So we have to get omega n squared here, right? So that's the problem here that we are facing. So now what we can do is we'll just break this into 2 parts, right? We'll just break this into 2 parts with this part in one corner and this constant in another corner, right? So we'll get 2s plus 1 on one corner, right? With the 4, and we'll get 10 over s plus 1 squared plus 4 in the other column, right? Now we'll compute them separately, right? Okay, so we are referring to the equations 20 and 21. Okay, if I share my table, so it's this and this. So we have to build our system in this form, and now you can get why I'm trying to get this format, right? I want a constant plus the s part, as well as I want in the 20 I want just the imaginary part, and the bottom has to be same, right? The denominator of these 20 and 21 transforms are the same, but the top is different. So I can write my system as 2 parts like this, right? You all get this, right? If you all are confused, let me know so I can re-explain. Okay. So I mean, for this part we can now we'll first go with this part, right? We first go with this part. So we'll name this as 1, right? So we'll get the 1 here using 20, okay, using 20 here. So for 20, what it states is we need omega over s plus. Sorry, this is actually for the other part. So we'll just we'll get this state is s plus a squared plus omega squared. So we have to build this in this format, and if we do that, we can simply substitute this. So we have the a and the omega, so we can just substitute this to this. Right? This is from the table, okay? Right. So we can get this 2 out, right? This 2 is not a problem because we have the linearity property of Laplace. We can just get this out. So we have the s here, and you can say that there's 1 here, and there's 4 here. Will this be a problem? No, right? Because our equation states we can have A here and we can have omega here. So these two can be different, but these two have to be the same, right? We have A in both these corners and we got that. We got A in both these corners and we got omega here, right? So there's no issue. So for this, we can just simply get A is equal to 1 and omega is equal to omega squared, right? This is omega squared, so omega squared is equal to 4. So omega is 2, right? The square root of this. So if we just simply substitute, so we'll write this as F1 is, right? So F1t would simply be, so is e minus e to the, so we got this two out, right? We got this 2 out. It's 2 t to the power minus a is 1. So I'm not going to write the 1 t. So this is one part, right? This one part that we require. Now we'll compute this part. I'll choose another different color so that it's like. So for this part, I'll use another color. So here for this part, we'll be using the relationship of this omega over s plus a squared plus omega squared is equal to e to the power minus at sine omega t, right? Now here you got to have omega and omega here, right? In the numerator and the denominator, you have to have both omegas, and you can have a here. So that is fine because we got a here and we got omega squared here, but we got to make this equal to this, right? We got to make we actually need to make this the square root of this because this is omega squared. So what we can do is we can get 5 out. Color. And just get the 5 out here. Can have 2 over s plus 1 squared plus 4, or we can just write 2 squared. Right? So we got this format. We have got the required format. So we know our omega. Omega is equal to 2. Omega squared is 4. A is 1, right? So we just have to substitute, and we'll get, if we write this as F2s, F2t is equal to 5e minus t, and we got what's our equation? Sine omega t, right? So this is sine omega is 2t, right? So I think this is fine, right? This is clear, right? Any of you all have any issues? Any of you all have any problems or any like concerns? So now this is not the final answer. To get the final answer, what we can do is we have to combine these two, right? So if I can like copy this part. I'll just go to the next slide, next page, so you can just like remember these two. So if you like you have a fun, you have a fun ds 2e minus t cos 2t, and you have f2t as 5e minus t sine 2t. So you get the final answer of ft as the addition of these two, which is, you get this part first, then sine minus t sine 2t plus minus t cos 2t. Right? So I hope that is also clear. So we have the final sum. So I'll quickly go to that also and we'll finish it off and we'll go to the next part. We're actually running out of time. So if I go to the next sum, anything unclear up to this point? Anything unclear? Yes?
No, sir.
Right. So we'll go to this part. So you can see here, it's there's actually like there's one in the numerator, but here there's another additional s in the denominator, right? So it's actually this, if you like multiply this, this is in the third order, right? So we'll do that. Also, this has so yeah, go there. So you write this down. 1 s squared plus 2s plus 2. Now you can see that this also has complex roots, right? If you like check this part, this also has complex roots because right, because this is 4 minus 8, which is like also once again b square minus 4ac is less than 0, right? So now what actually, once again, now if you look at the table, the format that we have to build this is simply the equation number 22, right? It's 22 would do, right? No, not 22, sorry. It's 24, right? So if we like get this format, I think we should be sorted, right? So you see this format. So there's an omega n squared on top, and here you have the bottom as s squared plus 2 zeta omega n s plus omega n squared. So if we get this format, we can simply substitute here and get the final answer, right? So we just prepare our equation accordingly. Okay, we'll go a bit fast now. We have like 2 more parts, main questions to cover. So we get omega n squared here, right? The omega n squared here, and in the bottom we got s squared plus 2 zeta omega ns plus omega n squared, right? So this is actually the format or the one that we got in the table. That's actually equation Laplacian transform number 24. So if we can like prepare it accordingly, I think I should be sorted. So already we can see that this is almost like sorted, right? Because we got if you look at the denominator, it's almost like sorted. We got a squared, we got 2s, and we got 2 here. So if we like get the omega n squared is equal to here, right? Right? So omega n squared is equal to here. Right? So omega n is square root of 2, right? Quite simple. And then this part, 2 zeta omega n, this is actually equal to 2s over here, right? 2 over here, because this is here, no? It's 2. Right? All right. So we got these parts. So this theta, right? This theta is actually what we call the damping coefficient. So this actually lets you know what sort of like the damping, whether it's underdamped or overdamped or like critically damped or whatever. So if theta is equal to 0, we call this undamped, right? There's no damping. If theta is equal to 1, we say critically damped. And if theta is less than 1, we say underdamped, right? Just keep that in mind, right? What theta means. All right. So in this part, in this one, we got 2 theta omega n equals 2. So if we like divide both sides by 2, we get theta omega n equals 2. So our theta is equal to 2 divided by 2, right? Because omega n is root 2. So root 2 is basically 1.4 something, right? So if I divide this, something like 2, give me something like 0.707, right? Like 0.707. So this system is underdamped, right? It's underdamped. And also now we can just we got our parameters. So we can simply substitute in our equation. So our equation is omega n squared over s squared plus 2 s plus omega n squared, right? Someone is asking whether theta is 1 over root 2. Is that so? Did I do a mistake?
Okay.
So 2 omega n is this is equal to 2, right? This is then 1. Yes,
2 is divided by 2.
yes, that's right. Sorry, this is 1. Thank you for pointing that out. Anyway, this is critical undamped, right? Underdamped. It's fine. Right. So yeah, thank you for pointing that out. Okay. So we have a system here. So omega n squared is equal to 2 omega n square root 2, and our this part. So omega n is actually we'll just put the 2 here so that it's much more easier for us to substitute simply 2, right? This because since this part is 1. So if we substitute into this, we'll get we'll simply get. So I mean, this is the format. So we got the format built. So to build the format, we have to go back and check out function. This now. So we got this. We have to get omega n square on top, right? So that means we have to get 2 on top. So we have to divide this by 2. So we can divide this our system by 2. But 2 on top, then we can get 2 on top. Have squared 2 plus we have 2 here, right? So here also we can substitute this entire thing is equal to 1. So we just got 2s. That's also fine. So we got our parameters. So we just got to substitute in our equation for this thing for 24. That is 1 minus 1 over square root minus theta squared e minus theta omega n t and sine omega n 1 minus theta squared t plus. So this phi is actually given by phi is equal to tan inverse 1 minus theta squared over theta, right? So you get the phi from here. You as you know this, you know theta. You can like one substitute them here, and also you can get phi from here and substitute here. Then you finally get the answer, right? So I'm not going to solve this. I just write you all the answer, the final answer, which I did last night. So you can like check the answer once you are done. So this will be the answer. Just let me know if you get a different answer like everyone, because I also like this a little while ago. I mean, so last night. So just check whether you are getting the same marks, right? Right? You all just submit your workings today. The one that you're going to submit today will not be marked. Okay, there will be no marks carried for that. This is just for me to like check whether you all have like got what we did today. Okay, so that's basically it. That's basically the first question number 1. So go to the second question. We have like half an hour's time, right? So in the second question, we have to model this. We have to solve this differential equation. This one, and we have the initial conditions: x0 equals 3 and x dot 0 is equal to 0, right? Okay, so we can do that. So we got 2x double dot plus 7x dot 0 to 0 equals to 0. Now initial conditions are I'll check that once this done. Okay. 3 x dot 0 equals to 0. Right? Usually we have the initial conditions as 0, but in this case we have the x0 as 3, right? So you feel like they can get Laplace, right? So we know that you all know from your mathematics that if you have like a function of x dot t, you get the Laplacian of this, we will get s6 s minus x naught, right? This is the initial condition. And if you have something like x double dot t equals s squared xs minus s6 naught, right? So usually if these are 0, you can just round it off for 0, right? But in this case we have x0 as 0, so you can't do that for this, right? And this too, right? You can't do it for this. But this, of course, you can round it off for 0. So this is generally the formats that we follow, right? Like this is like the Laplacian of the derivatives, right? This is the first derivative and the second derivative, which these are the Laplace. So for this question, sorry, just want to know this. Right. So for this particular question, we got this part. So we'll first write this 2s double dot. 2s double dot, we can write it as 2 squared xs minus sx naught minus s dot naught. I'll write line after another, so that's much more easier for us to check our values, right? So here we got the 7 plus 7 says xs minus x naught. Then we got our 3x here. The Laplacian of this would be 3xs is 3xs, right? Same typing will be equal to 0. So our function is sort of clear, right? So now to make it much more easier for us to like work with, we'll get the excess out, right? We'll get the excess out of this. So we get the excess of here out of the first part will be 2s squared plus here it will be 7s, right? 7s because this is the excess, sorry, 7s. In the last part it will be completely 3, right? Minus the remaining parts would be 2s6. So this we can like substitute 3, right? So this is 3. This is 3. So this is not 0, right? This is 0. I just substitute the initial values, okay? I think you are like familiar with initial value problems from your second year mathematics, right? So, right, so I got it. So if I like get this part, I got 2s into 3. Plus, I got 7 into 3, right? See. Okay, so we got this sorted. Now we'll simplify. Okay, so if we simplify this, we get 2s squared plus 7s plus 3xs here minus, or since there is 0, we'll just put it to the right. It's equal to 6s plus 21. Now, if we isolate xs, we got 6s plus 21 divided by 2s squared plus 7s plus 2. The point of me doing this is to get into something like this, so that we can get the inverse Laplace. Now we can't just this is in the time domain, right? Let's say this is like a second order differential equation, and this, let's say this is like let's say x is a position vector, so this is a velocity and this is a acceleration, right? So we can't put this in the time domain, frequency domain, and leave it there. We have to solve this, and then we have to convert it back into the inverse Laplacian format. So we have to like solve for xt, right? Solve for yt, right? So to do that, so that's why I'm like transferring this into this format, right? So I will go to the next part. So we got it. We got the excess isolated. So excess isolated, I write once again here. It's equal to 6s plus 21 divided by 2 squared plus 7s plus 3. So we'll get the 3 out of here, right? Since 3 is common for this top part. Right? It's 21. So we'll get the 3 out. So we'll get 2s plus 7 divided by 2s squared plus 7s plus 3. Okay. Now, if we divide the denominator, the numerator, but this is equal to plus 0.5. Yeah, square plus 7 divided by 2 will be 3.5s plus 1.5. So I just did that so that we can isolate s here, right? S doesn't have a coefficient, right? So now we can check for the roots of this, right? So this is simply like what we solved earlier, right? So we have like something like this: s plus a squared plus squared something plus s plus something, right? So we check by this omega I, we have to check the roots. If this is complex roots, this becomes omega I, like so, right? So in this case, you can see that this doesn't have complex roots, right? So here we have 3.5, and here we have it's not clear, so it's 3.5, right? It's 1.5. Right. So this is basically 7 minus 6 or something, right? So simply that means this doesn't have complex roots, so it's 8. So now this is in this format. Now we just have to find the inverse Laplace. So once again, we'll do the trick that we did earlier. We'll just divide this into 2 parts, right? We'll just get 3s over squared plus 3.5 s plus 1.5. And we'll get the other part as 10.5 over because we have to. Now we have this 3 out of the entire. If we are going to get the 3 out of here, if you are going to sorry. So we just took the 3 out here, right? That's there. We just took 3 out of this, right? This out of here, right? We had to put it here. I just missed that. So that's that 3 is here, right? But here also this is applicable for this part also, right? So I will multiply this 3.5 by 3 and put it here, right? So that is 10s divided by squared plus 3.5s plus 1.5. So if we get the roots, you will see that you will find the roots of this as minus 0.5 and minus 3. So I can write this as I'll just get the, I can write the excess as the 3 here is, so it's minus 0.5 and it's plus 3. And also this part we can write as 10.5 divided by s plus 0.5 and s plus 5. All right. So in this we know that a is equal to 3. This is, if you consider this is a, 3, and b is actually we have to check that with this thing. Check with this thing. No, we can't just define that. We just check with the table. Check with the table that we're using. Stop share to check for the table. Right, so we can go with this, right? We can go with this format. So we can define A and B, and we can go with this, right? So the screen. And so what we can do is we can get, let's say this is, let's say this 0.5, let's say 3 is a 3 now. Let's multiply with this, we get 3 now. This we can say is A, and 0.5 we can say is B, right? So A is equal to 3 and B is equal to 0.5. Right? Just check the workings, okay? I my handwriting sometimes I can't check, but actually I have written it. So now we got this. Now we just have to substitute in our equation, which we'll be using 16 for this, right? We'll be using 16 for this. We'll be using 15 for this, right? 16, 15 for this. And then we can get our YT. So I mean, based on the Laplace, inverse Laplace that we get as 3 1 over minus 2.5, 0.5. I'll try this in the next this thing. If we get the inverse Laplace, and we get 5t equals to 3 1 over minus 2.5 0.5 e to the power minus 0.5 t minus 3e minus 3t, right? So substitute on the equation 16 and 15 plus the other part 10.5 1 over 1 over 2 minus 2.5. We get e minus 3t minus e minus 0.5t. All right. So we if you simplify this, you will get this answer, right? You check the workings. Okay. I hope the method is clear. The workings, just check it once again. There might be some errors when multiplying and substituting, but I don't think there's any errors. But just check. Okay. Just check if this is the answer that you get. Even if not, if you get different answers, submit. I will check. I will review the workings. Okay. So we got 15 minutes to the last part. The last part actually, we'll try to finish it 15 minutes. But if not, you just go back and watch the recording. And if it's not clear, just let me know. I will explain it once again in another session. Okay. Okay. So we go back to a question. Question 3, actually here you have been given a transfer function, right? Ys over Rs, and it has these parameters. So you have to determine Yt. That means you have to get the inverse Laplace of this Ys part. You have to put this Rs to that side, and you have to get the inverse Laplace of this, right? Where Rt is a unit step function, right? So basically this Rs is a unit step function, right? So then you have to determine the steady state output, right? So we'll do this part. So we'll do the part A first. So I will write this equation. Try to this is actually important because I think you will have some stuff like this, right? You'll have some sort of like assignments like this in your assignment. You have like questions like this. So Ys over Rs is equal to 10 s plus 2 s plus 2 over s square plus 8s plus 50. right? So once again, when you have a function like this, I mean, before now we have to get yt, right? We have to find yt, right? So to find yt, you have to isolate yt. They have given us some sort of a hint saying that rt is a unit step. You all know how to define a unit step in the S domain, right? I think you all have done this in the lecture. So simply that means rs is equal to 1 over s, right? If you go to the Laplace table, if you check the equation, 1t is equal to, I mean, 1 Laplace of 1t is equal to 1 over s, right? So you can cross multiply this, right? You can directly put this s to the other side, because you can include this in the equation as an s. You can yeah. So what you can do is you can multiply both sides by rs. So you will get this 10 s plus 2 divided by, if you multiply this part also by rs, we just write this part as plus 15, and we have the unit step, yeah, 1 over s, right? Okay. So now what we can do is, now there are two options. You can either get this function inside and write it as this. You can write it as s plus 3 plus 5 and move out, right? The other way is you can multiply this entire thing, and then you can get a third order function here, and then you can find the partial fractions and then solve, right? So I will go with partial fractions method because it's much more easier, right? So 10 s plus 2. What I can do here is I can multiply this and write it as q plus 8s squared plus 15s, right? Then if you type this in your calculator and get the folds, you'll get 0 minus 3 and minus 5, right? So you can get 10 s plus 2 divided by, I can write it as I mean, so this is 0 means s, right? S plus 3 plus 5, right? Now you get the partial fractions, right? If you get the partial fractions and if you rearrange this, I will write the rearrangement. I mean, you can use both methods, but if you get the partial fractions and you rewrite this, you get something like this: 4 over 3s, this is the s part, 1 over s part, plus 5 over 3 s plus 3 minus 3 over s plus 5. All right. So now we can get the inverse Laplacian of this, right? Once again, the linearity property we'll be using. So let's write 4 over 3s plus, we can just write the 5 outside and get 5 over 3, right? S plus 3 minus 3 1 over s plus 5, right? All right. So we know from our table that when we have something like this, when we have something 1 over s plus a, we can write this as e to the power minus 8, right? So we can use that here, and here for 1 over s simply it's I mean 1, right? The if you like, it's the 1 noise is simply 1t or unit step. So this actually we call this something called the Heaviside function. I'm not sure that you have done this. You can write this as HTS. The Heaviside function is also something that we can call this, right? So this part, so this is basically, if you get the inverse Laplace in 4/3, you can keep it as just 1, or like you can put the Heaviside function, right? It's up to you. This is also correct, right? Plus, so this part is 5/3. 1 now is plus 3. We can write it as in this format because a is 3, e to the power minus 3t. And here we have this 3 here outside, and s plus 5 here once again. A is 5, so we can write it as e to the power minus 5t. Yeah. So this is actually our yt, right? It's actually our yt. So now they are asking for YSS, the steady state. Simply YSS is like we have as the unit step. I mean the coefficient of the Heaviside. So that if you like simplify, you will get something around 4 divided by 3 is around 1.33, right? So here you got that. So our first part is complete, right? Part A is complete. So we go to the part B here. Part B here. So part B is the different transfer function of the same. It's a different one. We are losing this as plus 2, and the denominator is changed. So here we have to like identify the system poles for unit step input and find output. Find unit step input and find output. For unit step find output. Then determine rise time, peak, overshoot, and setting time. Right? I'm not sure that we'll be able to complete this, but I'll do it. But if it's unclear, we'll have another session and discuss that, right? Okay, I'll quickly finish that also. So, do you all have anything after this? You have any other thing after this? Yes. Hello.
No,
I will take like maximum of 50 minutes of your break. Okay. I'll just to finish this off so that you all can like start with the time. Okay. Right. So I'll try to finish it within the time, but by any chance, if we go beyond. Right. So this is the function that has been given. Right. So to find the system poles. So find the system poles. So we have to get this, right? We have to get this. We get this. So you all know now from your complex numbers, you all know something like this, right? So like now this actually has complex roots, right? Because this is 20. This is just 2. So b squared minus 4ac gives you like 76, right? So minus 76. So that means this has complex roots. So you all know from your like complex numbers, if you like have something like this, let's say you have something like what? Like let's say now you all know this, right? X squared minus a squared, you can write as x plus a x minus a, right? But if we have something like this, x squared plus a squared, So what we usually do is, if we are allowed to use complex numbers, what we'll do is we'll just write this as x squared minus s squared, right? Then we can write this as x minus. So we'll just write this as just to understand much more clearly. It's minus square root of minus x plus square root of minus, right? So this minus we can write as x minus ai x plus a, right? So we are using the same theory here also. So what we can do is we can if you look at this, you understand that this part, this actually is simply, you can write this as square plus 2s plus 1 plus 90, right? So this is simply s plus 1 square, right? This part simply s plus 1 square plus 90. So we can write this using this technique. We can write this as s plus 1 minus plus 1 minus 90 square and s plus 1 plus minus 9. Okay. So this once again, so this is basically 19 into minus 1, right? So we can get square root 19 and we can get the minus 1's square root as I, and we can write this as s plus 1 minus square root of 19 I and s plus 1 plus square root of 19 I. So this is basically it's poles, right? So if you want to write the poles, that's the first question, poles. So simply you can get these as S1 and S2, right? So S1 is simply minus 1 plus I 19 and S2 is equal minus 1 right? The answer for the first part, right? So we have got the poles now. Now they have said they said that they are giving a unit input here, unit step input. Find the output, right? So we just multiply the entire thing, right side by 1 over s. So what we do is we just equals 1 over s, right? So if you multiply this. So what's the function once again? Function 10 over s square plus 2s plus 20, right? So is is once again, if you get is equal to 10 over s here square plus 2s plus 20, right? Okay, so now what we have to do is we have to get an idea about what are we going to match here, what are we going to target. So if you look at the table, Laplace table, look at the Laplace table here. We should actually try to map. Now this is just complex roots, right? So simply it's no point of looking at here. We have complex roots, so we go down. This, right? This is I think the most ideal that matches our setting, right? Right? So this actually we used earlier also. So we'll try to match that. So let's go to the whiteboard once again. So we'll try to map this. So so what we have tried to map here is this omega square divided by s square plus 2 theta s plus square, right? All right. So we know from this now we have to get these parameters. We need omega n squared. Omega n squared is simply 20, right? So omega n is square root of 20, which is equal to 2 square root 5, right? And then we need what else do we need? This part. We need this part. So once again 2 theta omega n is equal to 2. So once again theta is equal to this 1 over omega n is 2 square root 5. Tell me what this is. Root 5 is 4.47. Somewhere 4.4721. Okay. 4.4721. So we can just simply divide this by omega n to find our theta is equal to 1 divided by u 0.2236. So this is once again an underdamped system. Why it's theta is less than 1, right? So we got it here. Right, so now we got our parameters here. Now we can simply substitute, right? So and also we also now yeah, we can substitute, but also just know that there are some parameters that we need to find, right? There are some parameters that we need to find. So we'll do those when we get there. But still, to substitute here, we need. Do we have all the parameters that we need to substitute? Let's go to the table. All right. Yeah, everything is there, but we'll have to find phi. So phi is tan inverse this, right? So we'll have to find phi. This is tan inverse 1 minus square root of 1 minus theta squared divided by theta, right? So you substitute this particular value here and you will get an answer. Theta is equal to 0.2236. You get an answer here of 1.345 variance. Okay, I'm not going to compute this, just put in a calculator. 1 minus 0.23 divided by this tan inverse of that. Okay. All right, so we got all the parameters. Now if we go to this part, if we got this one. Now now we have to make this in this format, right? So we have to get omega n squared here, but we have 10 here. So to fix that, what we can do is we can put 2 out here and get it 20, right? Now we got all our I mean the entire setup properly. So we just got to substitute here. So I mean, after you substitute and find the inverse Laplace, I will once again write the answer. You check that once you're doing this. So if you just have to substitute, right? Substitute, you will get yt is equal to 1 over 2, that 2 here. Then 1 minus, because this is there in the equation, right? Just refer to the equation. This one is there in the equation. 1 minus, once you like compute 1 over 1 minus theta squared, it will give you 0 point, sorry, 1.026 e to the power. Here we have to write minus theta omega and t. So basically we know that theta and omega n is equal to 1, right? Because this is equal to this 2 is equal to 2 theta omega n was 2. So this is simply 1. So here simply the exponential function parameters here would be 1, right? Just check the, while I'm writing this, to just check the this thing, okay? What's there in the table, so you will understand. If not, you might wonder where these parameters came from, okay? And then there's a sign that's also there. So inside this, we have to write omega n square root of 1 minus theta squared t plus 5. So this will simply, once you substitute, it will give you 4.359 t minus 1.345. All right. So this is simply our function. Now we have been asked to find certain things, right? We have been asked to find. So we got the output, rise time, peak overshoot, and settling time, right? So we'll first go with the rise time. So we'll first go with the rise time. So simply rise time is given by, there's an equation for rise time. Right? So rise time is simply given by rise time is given by hold on a second. Yeah, so for these equations, I think you all have been given these equations. So rise time is given by this equation. PR equals 5 minus beta divided by omega d. And this omega d is different from omega n. Okay. So if you want to find omega d, just note this down, right? You might need this to find this. Omega d is actually given by omega n 1 minus square, right? You might need these equations, okay? It's rise time. I'm sure these are there. Probably this might be there in your slides, okay? And this is equal to this. Omega d is equal to this. So you can compute omega d. We got all the parameters to compute omega d, right? You got omega n. You got theta. You compute omega d. You put in here. But to find beta is simply tan inverse of your complex poles, that is square root of 90, right? That's what we got, right? Square root of 90. No? Square root of 90. So this will give you 1.345, right? So you got beta, you got this, you compute this. So it's 5 minus 1.345 divided by omega d. Omega d, if you substitute this, you will get you'll get 4.359. All right. So so you just substitute all these in this function. Now you got omega d. This is 4.359. You got beta is 1.345. At 5, and you just substitute. You get t. The rise time as 0.4125. Right. All right. So that's one. Then we have to find the overshoot. Once again, the overshoot equation is this. Overshoot equation is